Life on Earth is rich and diverse. It thrives in every corner of our planet, from the deepest oceans to the highest mountains. Nature has adapted to the most diverse environments. But what about life outside our home planet? Are there other forms of life somewhere in our solar system? Could microbes exist beneath the icy surface of Jupiter's moon Europa? Or are there traces of life on Mars? Join us as we explore the latest discoveries and theories about possible life on other planets. From the blue planet to the distant moons and planets, let's answer the question together. Are we alone in the universe? The vacuum of outer space presents a harsh environment, characterized by extremely low temperatures and high levels of solar radiation, which multicellular life cannot endure. While bacteria cannot thrive in such conditions, they may survive under certain circumstances. An experiment exposed certain bacteria to the vacuum for 3 years without any protection. The bacteria survived, with the outer cells dying and shielding the inner cells, which remained viable. This finding supports the panspermia theory, suggesting that life could travel between planets within meteorites. However, some astrobiologists argue that unprotected cell clumps would lack protection during planetary ejection and re-entry. An exceptional candidate for the possibility of extraterrestrial life is Mars. Mars is the celestial body in the solar system most similar to Earth, with a day almost the same length and an axial tilt that gives it similar seasons. There is water on Mars, primarily frozen at the polar ice caps and underground. However, several obstacles hinder its habitability. The average surface temperature is about -60 degrees Celsius. There are no permanent liquid water bodies, and the atmosphere is thin and composed of over 96% toxic carbon dioxide. Its atmospheric pressure is less than 1% of Earth's, and without a magnetosphere, Mars is exposed to harmful solar radiation. While no astronauts have visited Mars, rovers have studied it extensively, finding no native life forms. The source of methane detected in the Martian atmosphere remains unexplained, though non-biological hypotheses have been proposed. Mars may have been different in the past, potentially featuring bodies of water, a thicker atmosphere, and a functioning magnetosphere, making it habitable. The rover Opportunity discovered evidence of a wet past, but further studies revealed sulfuric acid contact instead of water. Although geological studies suggest Mars was once habitable, it doesn't mean it was inhabited. Finding fossils of ancient microscopic life is extremely challenging, even for Earth's earliest known life forms. Fossils require materials that preserve cellular structures and endure rock forming and environmental processes. Current knowledge of taphonomy, based on sparse Earth fossils, may not fully apply to the different Martian environment. Europa, one of Jupiter's moons, could be hiding a liquid ocean beneath its icy surface that may be a habitable environment. This potential ocean was first discovered by the 2 Voyager space probes and later confirmed by telescopic studies from Earth. Current estimates suggest that this ocean could contain twice as much water as all of Earth's oceans combined, despite Europa's smaller size. The ice crust is estimated to be between 15 and 25 miles thick and could be a barrier to exploration of this ocean, although it could potentially be penetrated by igneous columns reaching into space. Life would require liquid water, a number of chemical elements, and a source of energy. Although Europa may have the first 2 elements, it is not confirmed whether an energy source is also present. One possible energy source would be hydrothermal vents, but these have not yet been detected. Sunlight is ruled out as an energy source because it is too weak in the Jupiter system and would also have to penetrate the thick layer of ice. In contrast to the Earth's oceans, Europe's oceans would lie under a permanent thick layer of ice, which could make it difficult to aerate the water. Possibly the ice layer is not a homogeneous block, but renews itself in a cycle in which the surface ice is pushed down and eventually introduced into the ocean. This process would allow some air from the surface to eventually reach the ocean. This process would have allowed the emergence of life and the development of defense mechanisms against oxidation. The Europa Clipper mission, which aims to investigate Europa's habitability, is scheduled for launch in 2024 and is expected to reach the Moon in 2030. Titan, Saturn's largest moon, is the only known moon in the solar system with a significant atmosphere. Data from the Cassini-Huygens mission disproved the hypothesis of a global hydrocarbon ocean, but later demonstrated the existence of liquid hydrocarbon lakes in the polar regions, the first stable liquid bodies discovered outside the Earth. Analysis of data from this mission has revealed aspects of atmospheric chemistry near the surface that are consistent with, but do not prove, the hypothesis that organisms present there could potentially consume hydrogen, acetylene, and ethane and produce methane. NASA's Dragonfly mission is scheduled to land on Titan in the mid-2030s and deploy a VTOL-capable rotorcraft. The launch is planned for 2027. Enceladus, a moon of Saturn, has several conditions that could support life, including geothermal activity, water vapor, and possible subsurface oceans heated by tidal effects. During its 2005 flyby, the Cassini-Huygens probe detected carbon, hydrogen, nitrogen, and oxygen, all essential elements for life, in one of Enceladus's geysers emitting ice and gas. The temperature and density of these plumes suggest a warm, watery source beneath the surface. Among celestial bodies where life might exist, organisms from Enceladus could most easily spread to other parts of the solar system. Ganymede, the largest moon in the solar system, is unique in having its own magnetic field. Its surface resembles that of Mercury and the Moon and is likely just as hostile to life. However, it is suspected that Ganymede has a subsurface ocean where primitive life might be possible. This suspicion arises from the unusually high levels of water vapor in its thin atmosphere. Ganymede likely consists of several layers of ice and liquid water, with a liquid layer in contact with the mantle. This particular environment is considered potentially habitable. Callisto, a moon of Jupiter, has a thin atmosphere and a subsurface ocean, making it a potential candidate for hosting life. Its greater distance from Jupiter means it experiences weaker tidal forces, but also receives less harmful radiation compared to the other moons. Of all the Galilean moons, Io is the closest to Jupiter and has the highest volcanic activity in the solar system due to the tidal forces from the planet and its elliptical orbit. Despite this, its surface remains extremely cold at -143 degrees Celsius. Io's atmosphere is 200 times thinner than Earth's, and its proximity to Jupiter subjects it to intense radiation. It is completely devoid of water, though it might have had water in the past and potentially harbors life forms underground.